solution's right here. Now I have to resolve every single one. Oh my god. Time to get to work.
To solve this, we had to go to the golf course and physically measure the greens. First, we printed off an overhead layout of the greens and drew out our lengths in the form of an X and Y axis. Next, at every interval of 5 for the axis, including the endpoints, we created a point that lied on the perimeter of the green. After doing this, we visualized specific parts of the greens we thought could be modeled with an equation. Since the greens were very oddly shaped, we were forced into creating piecewise functions and dividing it into different regions with different areas. To do this, we first used a ruler to measure where each point would lie on the y-axis, then plug these points that we got into a TI-84. The calculator then gave us a scatter plot of the data, which we would have to manually apply a line of best fit for. Since all the curved regions were different shaped, we chose a function type that would be best represented for our data. After we did this, it was now down to calculating. The next step was the hardest and most tedious. To calculate the area of each specific region, we first found the integral with respect to x of each equation based on its two endpoints. This value would represent the total area beneath the curve. However, we didn't want this, so we had to use a horizontal value to split the green into two that we drew before in our calculation. If our calculated equations were above this horizontal value, we had to subtract the integral of this horizontal value from the integral of the equation, and if it was below the horizontal value, we would have to subtract the integral of the equation from the integral of the horizontal value. This process was the same for all 10 regions. Once we had the area of each region calculated for, we added each of the individual areas up to get the total area of the green and our answer to the posted question.
Finally, the perfect amount.